Hi, we're about to look at the first part of waves. What is a progressive wave? Well, it's one that transfers energy away from its source without transferring any material. Two examples of this would be electromagnetic waves. We know that these are progressive because they cause things to heat up around and about them. And we know that loud sounds make objects vibrate. Therefore, we can say that the sound waves are also transferring energy away from their source without transferring any material. Let's look at the shape of the wave and learn about labelling the various bits of it. So the amplitude is the distance from the midline to either the crest or to the trough. It's marked on the diagram with the letter small a. And the wavelength of the wave is the distance from crest to crest or from trough to trough. The time period t is the time taken for a whole vibration to occur, in other words, for one whole wavelength to pass. And the frequency measured in hertz is the number of vibrations per second. And we have a relationship between t and f, where t is equal to 1 divided by f. The phase difference is the amount that one wave lags behind another wave, and it's measured in degrees or in radians. Let's look at wave equations. The speed of the wave, well, speed is distance moved divided by time taken, and since the wave travels one complete wavelength in a time period t, then we can say that the speed of the wave, which we can denote as v, is equal to the wavelength divided by the time period, which is equal to the wavelength multiplied by the frequency. Now, waves can either be longitudinal or transverse. In a transverse wave, the vibration is at right angles to the direction of the wave. However, in a longitudinal wave, the vibrations are along the direction of travel. And you'll notice that you've got areas where the wave is compressed together and areas where it is spread apart, and the compressed bits are called compression and the spread apart bits are called rarefaction. Let's look at polarization. Well, a polarized wave only oscillates in one direction, and we can make a wave polarized by using a polarizing filter. So this is how we do it. On the left of the diagram we can see the incident beam. It's unpolarized and so it's vibrating in all directions. We pass it through the polarizing filter number 1, the polarizer 1. That's a vertical polarizer, and the light which emerges from the other side will be a vertically polarized light wave. Now, if we were to place another polarizing filter, which is polarizer 2, which polarizes horizontally, and we're trying to pass a vertically polarized light wave through it, then no light will be able to get through the second filter. It's interesting to note that materials can rotate the plane of polarization. Now, how do we prove that? Well, we repeat the experiment that you've just seen. So technically, if we put one vertical polarizer followed by a horizontal polarizer in the path of the light, then no light will emerge from the other end. But if we put a material in the path of the vertically polarized light, we actually do get some light coming through the second polarizing filter. And this could only have occurred if the material we've put there has rotated the plane of polarization. And that completes the end of part 1.
Created using Powtoon.